Alrighty, so I think we're going to get started. So we'll get started and finished with, so hopefully you grabbed the paper as you came in. So we'll be finishing the class with that. I think maybe we'll actually get out a little early today, which is like a little, we'll see if that actually happens. I'm not going to, I didn't make a promise. It depends on you guys. But we want the stuff that we're going to pick up next time. I think it's, I don't want to like just start it and then not have a chance to actually go into it. All right, we gotta go. Okay, so what we talked about last time, where we left off, was this kind of goofy thing that we called the stream function. And that's what we're going to talk about today. So the last, well, we had kind of two things that we talked about last class. We talked about how to think about conservation of mass for a differential control volume. And then we started this discussion about a stream function. And we defined this, so the variable that we use is psi. We defined the stream function in this really weird way. We said that the stream function is defined really by two separate partial differentials. So the partial of our stream function with respect to y equals u, and the partial of our stream function with respect to x equals negative v. Okay, so we have these two different ways of defining it, and it's two ways of looking at the same stream function. So what we did last time is we said, let's look at a specific velocity field, and if we find the stream function from one of these differential equations and then from the other one, these two things have to, by definition, match. So these are because there are two different ways of looking at the exact same single function, right? If you look back at our notes from last time, we kind of finished up with that, right? Okay, so we know that that this stream function is right, like two at a single function psi of x and y and potentially time as well. So it's going to depend on potentially multiple variables, but these are just two separate ways of looking at it. So this is, I guess, fine. It satisfies conservation of mass, which is a good thing, right? So it satisfies kind of our 2D continuity equation or conservation of mass. Right, because we could write conservation of mass would be du dx plus dv dy equals 0. So this would become d psi dx partial y minus d psi partial y partial x equals 0. So which is a true equation, right? It doesn't matter if you take the partial with respect to x first and then y, or y first and then x. Those are going to be exactly equivalent. So this satisfies conservation mass. So it's like this is an okay thing to do, but this doesn't really tell us why we would care. So let's look back and think. This is called the stream function. So you may think, okay, this may have something to do with stream lines. Yeah, Adam.
I think we wrote on Monday that it's d squared psi.
D squared, yes, that's correct. Because you're taking it with both x and y. Yeah, thanks, Adam. Yeah.
This for the conservation mass in the corner.
This was, yeah, so we did it for that specific example. This is general, this would be 2D conservation of mass. So we looked at the specific example last time of flow in a corner, and it worked out. But this is true of any velocity field. This top equation has to be true of any 2D velocity field. And the bottom equation is true just by like mathematical definition. Because if we take the partial with x and then the partial with y, that's the exact same as first the partial of y and then the partial of x. Just to say, like, we're allowed to define this goofy function like this, and we didn't break any rules. So it's okay that we did it. This doesn't have any like bearing on why we would actually do such a thing. It's just a weird math thing, right? So let's think about streamlines. So this is the stream function. Let's think back to a streamline. So in a streamline, right, that's something, I don't know, maybe it goes like that. Some line. Right, this streamline is kind of by definition tangent to the velocity field everywhere. Right, so we could pick out, say here, what the velocity is, and it's going to be that vector v. Okay, which is tangent to, if we looked at like a little snippet of our streamline, v is parallel to ds. Right, this is a little snippet of the streamline. That's how we were able to find streamlines and stuff from velocity fields when we did that before. That's just from the definition. We could write that, if we wanted to write that mathematically, this would be v cross ds is equal to 0, which in 2D is 0 equals, our velocity is going to be u I hat plus v j hat. That's our velocity vector, crossed with the streamline. So the size in the x direction, I hat, plus the size in the y direction, j hat. Right, just taking the cross product of these two different things. This is, we take the cross product, it's u dy in the k direction plus v dy in the negative k hat direction. So that has to be true. these are both, one's in the k direction, one's in the negative k direction, so we can kind of drop the direction part of it because everything's in k, and we could write, so u dy minus v dx is equal to 0. Okay. Oh, this should be x up here. That should be dx. Because it's like outside and then the inside. Right, if we set up like a table of I, j, and k, that's how I learned to do it. I think that's right. Yeah, so this is kind of the mathematical definition of a streamline. If we combine this with how we define the stream function, right? We define the stream function in terms of u and v. So we get what we'll call equation 1. So plug in for u, what was our definition of the streamline? That was partial of the stream, or the stream function, partial stream function, partial y dy, plus partial of the stream function with respect to x dx is equal to 0. So this equation is a different color. This is true along a streamline. Okay, so this equation has to hold. This is like kind of from the definition of the streamline, this has to be true as we move along a streamline. Because that streamline is always tangent to the velocity field, which is how we got this top equation, and then we just plugged in our definition. So this equation, true along a streamline. Let's look at a second equation. So that's our first equation. Now we're going to look, okay, so we'll look at just the stream function, and we'll take a kind of a snapshot. So we'll look at stream function, which is a function of x, y, and t. We'll take a snapshot at one instant of time, t0. So we take a picture of it, and then we look at how the stream function changes. So now we'll look at d psi. So how it's changing, it's not changing in time because we took just a snapshot. So it's changing only in x and y. So we could rewrite this. This is the change in psi in x plus the change in psi in y. Okay, so that would be just kind of mathematically how we would look at it. We'd say, how is the stream function changing? Well, it's changing in both x and it's changing in y. So you have to account for kind of both of those things. All right, mathematically, what does that mean? We could rewrite this as the change in the stream function equals how fast it's changing in x multiplied by how far you moved in x. So this would be d psi dx times dx. That's the change. Or just the change in x. And we could write the same thing plus dy times dy. So that's how much it's changing in y. So these are our two, we'll call this equation equation 2. Okay, so we have these two different equations. Equation 1 is true only along a streamline. Equation 2 is just generally true. That's just like a mathematical definition of the differential, of how this thing is changing. If we look at these two things together, they can tell us something about how, right, they look really similar actually. So we wrote the same thing on the top and the bottom, but in the top equation, we had this equal to 0. And in the bottom equation, we had this equal to the change in the stream function. So what does this tell us about how the stream function changes along a streamline? It has to be constant. So the stream function, so equation 1 and 2 together tell us stream function is constant along a streamline. Okay. Remember anything else that was constant along a streamline that we played with before? Remember how anytime we tried to find an equation for a streamline, like we found this streamline and then this streamline and then this streamline, there was always a constant involved in the process, right? You always had like, this is, y equals x over c, or y equals, c times x squared. There was always this like unknown constant c. Perhaps it's not just a random number. So this is like one of the reasons why we have this. Okay, so what is that constant c? Well, it's the stream function. They're related. So let's look again at what's happening with our stream function and streamlines, and kind of refresh our memory a little bit with some of that math. So we had for flow in a corner, we had this velocity field, v equals a x I hat minus a y j hat. So this is the example we started last time. We found that psi equals a xy plus c. Right, so this is, that's kind of where we ended. So we found that. We know that this value for c, this is an unknown constant of integration. We're going to give ourselves the easiest one that we could choose. So what's the simplest constant? 0. So let c equal 0. So that gives us psi equals a xy. We could rearrange this pretty easily. So we could write y equals psi over a x. And remember, or equals psi over a divided by x. And when we found streamlines, for this velocity field, we found y equals c over x. Okay. So we get the same equation that we like kind of in these two different weird ways. So c here is equals psi over a. So the stream function psi has kind of a direct relationship to this previously unknown constant c. But again, that doesn't tell us too much about why we care. So why did we do all of this math stuff? Right? Always a good question to ask. So let's look again at psi. So psi for this equals a x y. Let's look at the units on psi. So this has units of seconds to the -1, a would. Because again, if we go back up to our velocity, this has units, velocity has units of meters per second. X has units of meters. Y has units of meters. So that means this must have units of per second for the units to work out. So A has units of per second. X and Y are both meters. So that's a meter. That's a meter. So psi has units of meters squared per second. Or we can think about it meters cubed per second divided by meters, right? Those would be the same thing. This is just kind of a weird unit. And I'll explain a little bit why we would care about that. So let's look at a picture of what the streamlines are and the velocity field looks like. So our velocity field is going to be situated on some axes, x and y. It's going to have streamlines. The streamlines, we've calculated them before. We've looked at them before. These are going to be y equals c over x. They're going to be lines like that. So they're going to look, you know, coming down this way and kind of going out that way. And then there's going to be another one, maybe something like that. They're going to be defined by this unknown constant c. But now we know really they can be defined by their stream function value psi. So instead of saying like c equals 0.6, c equals 1, we'll define it just as psi 1 and psi 2. So that's going to be some number. It happens to have units of meters squared per second. So it's not a unitless number anymore. It's not an unknown. It actually has units, and it has these values. Each individual streamline is going to have its own value of psi. If we wanted to look at the flow rate, so if we wanted to look at flow, so let's say that this is kind of the direction of the flow. It's coming down from the top. And going that way. So there's going to be flow kind of down through the middle between those two streamlines. We know that, so the streamline velocity is always tangent to that, so there is no flow across a streamline. So what is the flow between the streamlines kind of down like that? Well, we could look at what the flow is, say across between any 2 points. So say between those 2 points, we could look at okay, if we looked at those 2 points, or if we looked at 2 points further down, or 2 points, for example, like if we looked at 2 points here, this one, and this one, and we looked at the flow across that area, those would, all of it would be the same. So let's look at, say this is down here, we'll call that X1. We'll call that X2. To find the flow, we would integrate the velocity over the area, right? Q equals the integral of velocity, the area, which in 2D, we could write Q over L equals the integral of the velocity d width. So this is the in, out of page, and that's like the width of the line over the whole line. Okay, so let's look first at our at the x direction one. At our top line, say we'll call this line up here, control surface 1, line 1. Okay, if we wanted to look at Q over L, that would be the integral from x1 up to x2 of our velocity field. So a differential width, that's going to be just dx, right? So that our differential width is just dx, because there's no y component to it, because it's a straight horizontal line. Okay, so this is going to be equals to the integral x1 to x2. We're going to plug in our velocity field, but we only actually care about the y component of the velocity field, because that's the only part that's actually going through our surface. The x component of the velocity field is going parallel to our surface, so that's not going to create any flow across that line. Only the up and down term is going to actually cross the line. So that's going to be v dx. Put a reminder. So only y component actually crosses the line. So if we did this integral, we could do that, but let's change it into an integral from x1 to x2. Let's plug in our definition of the streamline in for v, or our stream function, dx times dx. And now a really cool thing happens. This equals the integral, I'll do it down here. So Q over L is now equal to the integral from psi 1 to psi 2 of d psi. Right? Basically, that guy and that guy cancel each other out, and we're left with just d psi, which is everybody's favorite integral, because this equals just psi 2 minus psi 1. So psi 2 and psi 1 have units of equals like delta psi, which has units of meters cubed per second per meter, just like flow rate does. So psi, this stream function, it's a way to basically, we could do the same thing if we looked at the, say, the flow across the y, like from y1 to y2 across this guy. It would give us the same result. Across 2, where it's just equal to the like psi of one streamline minus psi of the other streamline. So you can directly find what's the flow rate between any two streamlines. It's always going to be constant. We can find it between two streamlines if we can figure out the psi value, which is fairly straightforward to do. And that can give us directly what the flow rate is between those two streamlines. So you could plot from a velocity field, you could plot streamlines where they're spaced so that the flow rate between any pairs of them is always constant. So rather than just like guessing it and just kind of getting an idea of the shape, this would give us a way to say, you know, I have streamlines of like psi 1, psi equals 1 meter squared per second, 2 meters squared per second, 3 meters squared per second. Those would be spaced evenly apart by flow rate. So it's a way to be able to like plot and visualize some of these flows from the velocity fields, be able to connect flow rate and streamlines and all of kind of a lot of different parts of these kind of concepts. Adam, did you have a question?
Yeah. Before we cancel out the dx, there's a negative on the d side. Does that go away because our flow is going in the negative direction?
So this should be, so it's because it goes away because the flow is going down. So I should have plugged in here. I should have plugged in negative v there because that was, I should have plugged in like this is v, but it has it, but I'm going, because the flow is going down, it should have been, I should have plugged in negative v crossing that. Yeah, you're right. Okay. So some kind of weird math stuff, but it will help us when we start. It'll be a little bit, maybe on Monday when we bring some of this stuff back up and look at how it relates to yet again, how it can relate to helping to visualize what a flow field looks like. But it's a way to connect like the streamlines that we have to what the volumetric flow rate is, kind of directly, and get a little bit more meaning into the unknown constant C. So that's all I have for today. So there's the sheet that you passed, that I passed out. I don't think it'll take, we have 15 minutes left. I don't think it'll take that long, but if it does, that's fine. This will be due on Friday. So it should be a good step in the direction of getting this next homework assignment done. So we'll spend the last bit of class working on that handout.